Good morning, ladies and gentlemen. On this last session of the SCI Cafe for the academic year 2021-2022, it's a great pleasure to have with us a very distinguished scientist from Greece, from the physics department of the Aristotle University in Thessaloniki, Professor Panos Patsalas. Professor Patsalas will discuss today with us. The title of his colloquial talk will be a frank assessment of ceramic conductors as an alternative plasmonic materials. Few words about our distinguished speaker today. He has received a bachelor degree in physics at the University of Ioannina in 1996, PhD in solid state physics with a great distinction at the Aristotle University of Thessaloniki in 2001. He is a visiting professor in Nottingham Trent University in the UK. He joined in 2004 the Department of Materials Engineering at the University of Ioannina as an assistant professor. And then in 2013, he joined the Department of Applied and Environmental Physics within the Faculty of Physics of the University of Thessaloniki, Aristotle University of Thessaloniki, as a professor in 2013. His research activities include growth and processing of thin films and nanostructures by various laser PVD and CVD techniques, and study of their electronic properties. His work has received more than 6,000 citations, and his age index is 46. So for our university, for our event, his participation is a great pleasure and a great honor. So Panos, since you have let me to call you Panos, me and George Kavoulakis as the organizers of this event, and as a part, on behalf of our university and our community, we would like to thank you, and the floor is yours. Thank you.
Thank you very much, Kostas, for the introduction. It's my pleasure to be among very good friends today. So really, I'm very, very happy. Let me share my screen in order to show you my PowerPoint.
You have the option. Thank you. Yes.
Yep. Thank you. Subtitles. So, the title of my talk today is a frank assessment of ceramic conductors as alternative plasmonic materials. And one of my colleagues here in Thessaloniki that has received the invitation by Facebook asked me yesterday, why frank? So let me clarify this first. Is because we are in a scientific cafe among friends and so on, I would like to discuss not only the perspectives and the good things about ceramic conductors as alternative plasmonic materials, but also the problems, because there are a lot of problems with these materials. So that's why I introduced the frank before the assessment. Because usually all of us, we are trying to promote our work and show that what we are working with is fabulous, very interesting, and so on. And sometimes we skip the problems. So I will focus to the problems as much as to the perspectives of these materials, and that's why I use the frank here. So what I will show you is the result of the work of a lot of people from a lot of places. I indicate here are mostly my direct collaborators in Thessaloniki and the group leaders of many groups that we have collaborated and that I included their works here. Of course, there are more people from each group. I have screenshots from the papers. So you will see the other authors as well. So what I will review today actually is not our work alone, but the work and the effort of a wide variety, a wide network of people for whom I'm very grateful, because without their collaboration, we wouldn't be able to proceed with our research. So I will, since we are in a colloquium, I will make a short introduction about plasmonics, because maybe we will have some students among us and they would be interested to be introduced in this field. Then I will try to show you why do we need alternative plasmonic materials and what are the best candidates. And then I will focus to the optical properties and the plasmonic performance of binary and ternary nitrides and the identification of trends from the literature. Then we will go to the problems, as I mentioned. So we'll discuss about the defects, and because these materials actually, they have a lot of defects for reasons that I will explain. And so the defects are very much correlated with the growth. So there are severe implications to the growth of these materials. And the last part is to show you some quite recent attempts to produce plasmonic nanostructures of conductive nitrides with processes that are characterized by high throughput. What are plasmonics? Plasmonics actually are photonics with metals or metals in general, so conductors in general, because as the title of my talk says, the metals can be also ceramic conductors. So the electromagnetic waves actually couple with the free charge density oscillations because of the free carriers in the conductors. That means that we have an epsilon1, the real part of the dielectric function, that is a negative up to a certain value, which is called the plasma frequency, and then gets a positive value. And actually this crossover frequency or crossover wavelength is roughly where the plasmonic phenomena will occur. It does not coincide with the maximum of the plasmonic effect, but indicates the spectral range where we would expect with a deviation of a few nanometers or a few tens of nanometers if we are working in the visible and UV range. So for the metals, for frequencies less than this plasma frequency, we have a very high reflection. For frequencies higher than the plasma frequency, we have mostly transmission. So it's like the material, the metal material or the conductor material becoming transparent material. And exactly at the plasma frequency, we have longitudinal waves of the electrons in the material, in the conductor. So the traditional metals that are used for plasmonics are mostly silver and gold. Silver is the best in terms of performance, gold is the best in terms of stability. And there are some emerging materials like the nitrides of the transition metals of the groups 4B, 5B, mostly 4B and 5B. That means nitrides of titanium, zirconium, hafnium, vanadium, which is not so stable, niobium, tantalum, molybdenum and tungsten. The nitride of chromium is semiconductor, it's not conductor, so it's not considered in this talk. And also, more recently, some materials based mostly on zinc oxide, the transparent conductor oxides, which are actually doped zinc oxide with aluminum or with gallium or and so on, and also indium tin oxide. This category of materials, I will show you later, are also considered as ceramic conductors as well, and alternative plasmonic materials. So actually the plasmonics is the science and technology of metallic nanostructures interacting with light. The optical properties of nanostructures are substantially different than their bulk counterparts. So you can see here a bar of silver, which has the well-known shiny silver color, and a bar of gold. But if we have colloidal silver or colloidal gold, you can see that the optical appearances is very, very different. And in addition to the scientific interest, this is also an emerging technology that has or promises to have a very good perspectives in terms of economic implementation and viability. So it has been included by the World Economic Forum as the top 10 emerging technologies in 2015. Okay, there are a lot of different kinds of plasmons in the metals. That is because of the different geometries. So the bulk plasmon is when we have a 3D material, so bulk material that interacts with the external electric field that induces oscillation of the free carriers. And this, when we are at the plasma frequency, we have a self-sustained longitudinal charge oscillation. And this is quantized. That's why it's called plasmon. It's like having a particle. And there are a lot of papers, mostly involving experiments of electron energy loss spectroscopy, where we see this quantization of the plasmons. One of a lot of papers is ours, where you can see the number of quantized plasmons in various transition metal nitrides in electron energy loss spectra. The second case is the so-called surface plasmon polariton, which is a propagating wave bound on a metal dielectric interface. So actually here we have a 2D nanostructure and we have an increased electric field and near field at the interface. And this extended near field is what helps us to implement such structures for biosensing, for example, as I will show you later. In order to have this surface polariton, plasmon polariton mode, the dielectric function of the metal should be less than minus the dielectric function of the dielectric. And the third case is the localized surface plasmon resonance, which occurs in metal nanoparticles because, again, of the oscillation of the free electrons in the nanoparticles, which are bound by the dielectric environment. In that case, we have a maximum at the frequency which is defined by this equation, and and why is that? Because actually we have when we have the Froelich condition, the so-called Froelich condition, that means the real part of the dielectric function of the metal is minus 2 times the dielectric function of the dielectric medium. Here, then the denominator is becoming 0, and so we have actually an infinity of the reflection, for example, for the far field. In this resonance frequency, which is of course does not go to infinity because there is some dielectric loss and electronic loss, there is some damping here. We have strong scattering, strong absorption, and strongly enhanced near fields. So actually, one of the results of my talk will be, as you will see, that the third feature here, the strongly enhanced near fields, is not present in the alternative plasmonic materials. So this is the first frank statement, okay? So because we have this resonant behavior, we have selective reflection and transmission. So we have coloration of the plasmonic structures. This is well known from the antiquity. This is the Lycurgus cup from the British Museum, very well known. And also the stained glasses, the big rosette from the Notre Dame de Paris here also is because of plasmonic nanoparticles embedded into silica glass. Here also you can see some coloration of assemblies of silver nanoparticles that they have been produced by laser annealing. Actually, And you can see that by changing the conditions of layers annealing, we can have the full color palette from red to blue and cyan and so on. And also here you can see some features produced by photolithographic masks. This was deliverable for the Marie Curie project of Nicholas Kalfagiannis in Nottingham-Trent. That's why we selected Marie Curie for the demo. And also because we called this process Mona Lisa, we also selected Da Vinci's Mona Lisa as another demo of the technology. So you can see actually all these pictures are assemblies of nanoparticles of different sizes that they have different resonance colors. So we change the particle size and then we see the different colors in our assembly. So about the applications for the surface plasma polaritons, the most well-known application is the biosensors. Also, they are used for sub-wavelength waveguides. And for the LSPR, they are used for laser technology in various forms. Also, they are very promising for photothermal therapy. Actually, currently, we are running 2 ELITech projects for photothermal therapy of cancer with plasmonic nanoparticles in our lab. And also, we can have biosensing, as I told you, with surface enhanced Raman scattering being one of the candidate techniques for these applications. So if we see the spectral requirements and we see where we do have some transparency windows, so the silicon transparency is from the near infrared to the mid infrared and overlaps with the telecom window, which is from within the near infrared here, and also the biological window, which is again in the near infrared but closer to the visible. So we are particularly interested in these two windows, the biological window, the telecom window, because of the various applications. Apparently, we do care about the biological window for the photothermal therapy of cancer, and the telecom window for applications in telecoms. So, as I told you, the mainstream plasmonic materials are mostly silver and gold. And indeed, silver and gold, although the spherical nanoparticles of silver and gold have some resonances which lie exclusively in the visible range, they can extend to the near infrared and mid infrared if we change the structure, the morphology, the shape of these materials. This has been shown by the Hallas group 15 years ago. Not only Hallas group, but this is a very clear picture of what is going on. And the problem with that is that the complex shapes of silver and gold are unstable in strong electric fields, because both silver and gold, they have relatively low melting points. So if we illuminate with a strong laser beam, they have the tendency to melt and reshape in nanosphere structures. So actually, sorry to go back, you can see here this from this work from Harald Gissen's group from Stuttgart, exactly these. These are nano antennas of gold that after having interacted with light, they have lost their shape. And so you can see all these irregular shapes here. And actually in this particular paper, exactly the group from Stuttgart have shown that if we replace gold by titanium nitride, which is a refractory conductor, then the antennas can sustain the high electric fields. So the more uneven is the shape, the less sensitive is to the strong electric fields. So another issue is that very elongated nanoparticles are toxic for biomedical applications. So there is a tendency of the liver to capture all elongated nanostructures with archetypical example, the carbon nanotubes, which are extremely toxic for this reason. And so the liver captures these elongated nanostructures, but these are toxic for the liver, so it can promote liver cancer. Also, silver and gold are not CMOS compatible exactly because of their relatively low melting point. So their growth is not compatible with CMOS devices, especially for very important. So we were looking for other solutions to tune the LSPR with materials that can endure the high electric fields and change the spectral range, not due to the shape, but due to the density of carriers in these materials. So the issues that we had to think about were the carrier density, which is the most essential, and the carrier density actually defines the spectral position of LSPR in spherical shapes. We have to take into account the electronic losses, which is one of the drawbacks of the alternative plasmonic materials, the dielectric losses, and also we would like to have some desirable features such as the CMOS compatibility, refractory character, and durability at high temperature and high fields, surface functionalization potential, if possible, and work function tunability if we want to have emitters of hot electrons. So what does it make a good optical conductor? Okay, in this slide, I have a quite detailed discussion. I will not go into detail here in the talk, but later, if somebody is interested, can look into this slide. Actually, a good electron conductor is a material that for a desired spectral range has a switching behavior from negative to positive values of the real part of the dielectric function. And actually, the steepest this change, the more sensitive to, for example, for sensing and so on, would be the material. Actually, it means it's less lossy, but okay. So we are looking for materials that they do have this switching behavior from negative to positive values of the real part of the dielectric function. The nitrides of transition metals, interestingly, are better optical conductors than the metals themselves. So if we want to go to alternative materials, it is more wise to go to their nitrides instead of going to the metals themselves. So one idea for the alternative plasmonic materials is to use the conductive nitrides of these metals, as I already told you. And I will show you that we can have some resonances from the far UV from around 150 nanometers to near infrared. All these materials are very refractory and they are very durable to high fields and high. And the other option is to go to transparent conductors, transparent conductive oxides, which is indium tin oxide, aluminum doped zinc oxide, gallium doped zinc oxide, and indium gallium doped zinc oxide. You can see here that these materials are mostly operating in the infrared from the near IR to mid-IR. They are printable materials, so there are a lot of perspectives in terms of fabrication, scaling potential, and so on, but they are less thermally stable due to the doping diffusion. So about the transition metal nitrides, the good thing about them is that is a category of materials that is very well studied for other applications. So we know them very well. And also, as you can see here in this figure, they have a very extended phase space of lattice constant and carrier density. So by changing the carrier density, we can change also the LSPR frequency and wavelength. So they are characterized by high hardness, chemical stability, and they are all refractory. So they have melting points, all of them more than 3000 Kelvin. They are electron conductors, so they have been used for electronic applications, other electronic applications apart from plasmonics. And the archetypical examples are the titanium nitride and zirconium nitride for mechanical applications such as hardened wear-resistant coatings, and titanium nitride and tantalum nitride for applications, so for electronic applications such as Schottky contacts, diffusion barriers, Schottky contacts on silicon, diffusion barriers in integrated circuits, and ohmic contacts on gallium nitride, and so on. So there is it's very expected. We were expecting that with so many nice properties, these materials would be considered for plasmonics. The group from Purdue, they have promoted very strongly these materials, and actually I would dare to say that they were the first to have a so ambitious strategy with these materials, and helped the entire community of alternative plasmonic materials and to work into these materials. So you can see a lot of works from a lot of groups for different applications. So we have reviewed the dielectric function of all these materials from the entire literature. So we have gathered data from groups worldwide grown by various techniques. In this review paper, we present all these comparative work. And so we have seen that the variations here of the crossover wavelength and frequency, where we expect to have the LSPR, and in the different materials, and also how steep is this behavior here is an indication of the electronic loss. Then we applied some Maxwell-Garnett effective medium theory calculations based on these dielectric functions, and we try to identify what the nanoparticles of these materials would look like. And so you can see again that we have some LSPR in all cases of the group 4B and 5B nitrides. Interestingly, zirconium nitride seems to be a better plasmonic material than the most well-studied titanium nitride. And also for the UV applications, it seems that the tantalum nitride and tantalum nitride and niobium nitride are the two candidates. And after this review paper, we made an extraordinary experimental work that we wouldn't expect. And it's the case of the molybdenum nitride, which is not included in this review at that time. And we realized with very detailed experiments and very detailed DFT calculations that were carried out by our colleagues in Rensselaer Polytechnic Institute in upstate New York, that actually the defects in molybdenum nitride are helping the plasmonic performance. That's why I'm calling the case of molybdenum nitride an extraordinary case. So the defects, instead of producing damping, they help the material to perform better in the UV range. And so we have some resonances as low as 150 nanometers in the far UV. Also, we can tune the LSPR by ternary nitrides. So by blending the various metals, we can go either to UV. So by blending, for example, titanium nitride with tantalum nitride here, we can have this variation from the visible, you see from actually green to near UV, while if we blend the titanium nitride, titanium with aluminum or scandium, or more recently with magnesium, we can have a shift towards the near infrared. And these are more detailed calculations for the binary nitrides here. So you can see how we can actually cover an entire range, and actually our current projects are focused to optimize the growth of nanoparticles for the near infrared range within the biological window for the therapy of cancer. So how do these materials compare to the traditional silver and gold? If we compare the far field properties, we can see the optical absorption, the epsilon 2. You can see that actually titanium nitride has a more, not more strong, comparable in terms of strength resonance with gold. So this is titanium nitride and this is gold. And also it has a less dielectric loss overlapping with the resonance. So gold has this dielectric component where for titanium nitride this is very clear, but the resonance is wider. So this is a first hint, a first indication that this material would not have a very strong field and near field enhancement, and so maybe it wouldn't be the best case for sensing applications, something that we later have confirmed. Also very interesting, the zirconium nitride. Here you can see that it has a resonance to a shorter wavelength. So we are in the blue range instead of the green range. And the resonance is much stronger than gold. So zirconium nitride can be an alternative plasmonic materials that could beat gold in any comparison, and still having the good refractory character and so on. Still, it's a lot inferior to silver, as we would expect, at least in terms of plasmonic performance, because of course in terms of stability and so on, it's better than silver. So what about the near field enhancement? So the prediction from the far field spectra is confirmed by finite difference time domain calculations made by the group of Lefteris, Lidorikis, and Yanema. And so you can see that all these materials are inferior to the gold, which is already a lot inferior compared to silver. So actually, and this is the frank assessment, we have very strong indications that, as I told you, were confirmed later by experiments, that the near field enhancements in these materials are not so good. And so for sensing applications or any applications that the near field enhancement is essential, are not as good candidates as we would expect when we started working with these materials. So what we have discussed so far was about almost perfect materials, the best cases, because we use the dielectric functions of optimized films and so on. But when we go to nanostructure fabrications, we have a lot of defects. And this is a crucial difference for these materials compared to gold and silver. Like gold and silver, these materials can have a lot of point defects. And we have seen that by Raman spectra, I will show you later. And that means that we have to be particularly cautious when we grow these materials in order to control the defect density in the nanostructures. So actually, the refractory character, which was supposed to be a blessing because it provides the so desired stability, at the same time is a curse. Why is a curse? Because when we are dealing with refractory materials, then during the growth, there is a spontaneous formation of point and extended structural defects. So the point defects in titanium nitride, we have this studied this since 2001, more than 20 years now. So the point defects, they scatter the electrons and trap them, so they can affect the carrier density as well. That's why many groups reported titanium nitride with plasmonic behavior in the near-IR range instead of green. Also, we have the extended defects, which are exclusively scatter the electrons. So if we compare these two types of defects, we would, and we cannot avoid having some defects in our films, we would be more happy with having extended defects than point defects. We have shown this in a recent work in collaboration with people from Purdue and from France and from New York, who were very kind to provide a lot of samples. And the people in Purdue, they have done some very nice infrared characterization. And we have seen in the Raman spectra that there is a clear scaling of the Raman spectra, actually the first order Raman features here, which are usually forbidden because these materials are centrosymmetric. So we shouldn't measure these materials unless we do have structural defects that break this symmetry. And so we have seen that the strength of these otherwise forbidden peaks are scaled very well with the energy of vacancy formation that was calculated by DFT calculations in Rensselaer, as I told you. So you see that indeed for titanium nitride and zirconium nitrides, especially titanium nitride, the contribution is minimal, while for tungsten nitride, we have a lot of point defects, both at nitrogen sites and the tungsten sites. And that's why tungsten nitride, although it was predicted for the perfect crystal of tungsten nitride that this would be an ideal UV material, we have never achieved in the experiment to produce a decent tungsten nitride plasmonic, UV plasmonic conductor. Because always we had a lot of defects in these materials. Another very interesting thing is that in sputter deposition, by changing the bias voltage, we can switch from conditions that produce point defects to conditions that produce extended defects. And as I told you previously, we were amazed that when we have extended effects, we have the signature is of these TA and LA first order peaks in Raman spectra are less pronounced, and the plasmonic behavior is better. So that means that by having this negative bias voltage, that means giving a lot of kinetic energy to the depositing species, we have an annealing out of defect to the grain boundaries. This was an amazing discovery that we wouldn't expect, that the epitaxial nitrides are not necessarily optimal for optical or plasmonic performance. Because in epitaxial nitride, we do have a lot of point defects for strain relaxation. While for polycrystalline materials, we can have this annealing out of the defect to the grain boundaries and have an improvement of the plasmonic performance. This was something that we wouldn't expect. Actually, when we were discussing this in Purdue and some years ago, and I told them that I have the intuition that this is the case, they were so thrilled that they said, okay, can you prove it? If you can prove it, this would be very, very interesting. And indeed, with the help of the Raman spectra, we were able to prove this quite recently. So having all this in mind, we try to exploit all the knowledge that we acquired all these years working with these materials and having understood quite well what are the effects of point defects and so on. And so we try to have some high throughput fabrication of plasmonic nitrides. And I will show you some very, very recent attempts from last year. So it's about some self-assembled by glancing angle deposition linear nanostructures here. This is the first case, and I say that this is for high throughput because you can see that we do not involve electron beam lithography and so on. And so we have some homogeneous, okay, dichroic, but homogeneous in the one direction growth of macroscopic samples. So you can see exactly the size of the sample compared to a $250 and €1 coin here. And here are the nanostructures as grown. So you can see here the titanium nitride and zirconium nitride, the linear nanostructures. I don't say nanowires because they are not so homogeneous. And again, you can see here the Raman spectra to evaluate their crystal and the existence of defects, and also the identification of the phase. You have indeed zirconium nitride and titanium nitride and not pure zirconium or titanium. But the most important is the performance. So you can see here the very strong dichroism because of the different plasmonic conditions in the two directions of the electric field. And this was more impressively demonstrated by second harmonic generation measurement carried out in Heraklion from Manolis Stratakis group. Manolis is with us. I don't know if Sotiris is with us, Florian Drakopoulos, who was responsible for these measurements. And so we can see that, and this is really amazing that we have a different polar figures for zirconium nitride and titanium nitride. Why is that? Because actually for titanium nitride, we have quite homogeneous linear nanostructures. So we have plasmons only across the linear nanostructures, while for zirconium nitride, the nanostructures are not so homogeneous. So it's like having a beads of zirconium nitride. It's like a convoloi of zirconium nitride. So actually we do have plasmons both across and along the linear nanostructures. And because the nanostructures along the beads, along the nanostructures are in the correct wavelength for the second harmonic generation, we do have this direction of the second harmonic generation, while for titanium nitride we have the vertical one. The second case is to produce titanium nitride nanostructures by nanosphere lithography, which was not trivial at all, because for sputter deposition, we do not have so strong shadow effects as in the case of evaporation, either electron beam or thermal evaporation. So usually, what you get when you sputter deposit any kind of material through the polystyrene mask here is not having the desired triangular islands of material, but instead of that, you have continuous meshes of material. For some applications, this is not bad. This is not bad at all. But for our application, we would like to have the isolated triangular islands, nano islands. So what we have done, actually, we used some oxygen plasma pretreatment of the polystyrene mask before the deposition of titanium nitride in order to close this empty space and promote more the shadow effects. So by actually flattening the polystyrene beads here, the polystyrene nanospheres, we let very, very small space for the depositing species to pass through. And with this process, we were able indeed to produce triangular shapes instead of continuous meshes here. And you can see exactly the size of these triangular shapes. And the very good thing about that is, again, we measure the Raman spectra, and we realized that in terms of point defects, these materials with the optimized conditions to be polycrystalline and not epitaxial, they have a very, very good behavior. That means very low point defects. And also we detected some carbon, which has actually located inside this pattern of the nanoislands. So it's like having a residue of polystyrene, which is amorphous carbon here, which is surrounded by the plasmonic nanostructures. And this is very funny and might be interesting. We still don't know, because carbon it has a very strong biofunctionalization potential. So we could isolate some kind of biomolecules here and so on. These nanostructures are very interesting that because of the spikes that they do have, these triangles, and because of the irregular shape, because they are not spherical, you can see that they have some resonance, or they are predicted to have some resonances in the infrared. So here you can see that, that the resonances are around 2 microns. The near field enhancement is not that much as predicted, as expected, so not predicted, as expected. So again, the Frank statement, very interesting far field properties, but very poor near field properties. And the third case, which is actually what we're working now, is colloidal titanium nitride. And we're working this because we should eject this colloidal titanium nitride into some mice or whatever for the cancer treatment. The good thing is for the laser ablation in liquids that they can produce nanoparticles of any binary or ternary nitride. So actually our strategy is that we are producing thick films of binary or ternary nitrides. That means that we can tune exactly the composition and of our target, and we do not rely to commercial targets alone. We do grow our own targets, and then with laser ablation in liquids, we can produce nanoparticles of, in principle, of any nitride. Here you can see the differences of some of our nanoparticles produced by picosecond laser beam to particles in the literature for nanosecond laser beam, both in aqueous solutions. The nanoparticles, if we take into account the absorbance, the resonance is very, very faint and redshifted. So we have redshifted means that we do not have as many carriers as we would expect for a pure titanium nitride. And so the nanoparticles are defective. And if we compare the Raman spectra of the nanoparticles compared to the linear nanostructures grown by glancing angle deposition and the nanosphere lithography, polycrystalline titanium nitride film, epitaxial titanium nitride film, you see indeed that the signature here is very, very, it's quite bad, not very, but it's quite bad. And here are surface oxides. So this big here is for a surface oxide, as presented by Zanki, Nange, van de Hemi. So actually what we do believe for our materials is that they are actually like core shell structures with a core of titanium nitride and a shell of titanium oxide. Okay, we have some strategies to avoid that by changing the environment of ablation. Still, we are not quite sure that the oxide is bad, because titanium oxide is very good biocompatible material. So having a core shell structure, since we do not care about the near field enhancement, and we only care about the photothermal absorption and increase of temperature, this oxide shell might not that bad as it seems in this spectra. So to conclude, I have shown you that the B1 means the rock salt structure, transition metal nitrides, are better optical conductors than the corresponding metals. They combine tuned carrier density with refractory character, CMOS compatibility, and so on. So there is substantial variation of the carrier density for both binary and ternary nitrides that allows us to cover a very wide range from the far UV to the near infrared. And let's go to the frank statements. The near field enhancement in this material, even for perfect nitrides, is inferior to gold. So no applications where the near field is essential, like surface enhanced Raman sputtering or other biosensing, is suitable for these materials are not suitable for any application where the near field is essential. And the far field's performance can be comparable to gold and silver. So there are some good perspectives for applications involving the far field properties at elevated temperatures. So photothermal cancer therapy, hot electron chemistry, photocatalysis, and so on. So these materials are not rubbish, but they have a certain range of applications. So there are a lot of issues to be solved for a high throughput fabrication of such plasmonic nanostructures. And so we're working a lot on that in order to be able to provide high quality, high performance nanostructures of such materials. And with that, I'm thanking you very much for your attention, and I'm ready for your questions.
Thank you very much, Panos. Very nice work. Very nice physics. And I will give the floor now to the audience. If there are any questions from the audience, please raise your hand in order to direct the question to our speaker. So we have, at the same time, I don't know who was first, but I will give the floor hierarchically. So I will give the floor to our Vice Rector Papadogiannis first in order to
Giorgos.
No, I am on charge. I'm on charge. So I'm on charge, so I will do the ways, as I wish. So the floor is yours, Nectarios. Please direct your question.
Nectarios comes first.
There is no negotiation.
Okay. Thank you both. Panos, thank you for a very exciting talk and very well organized ideas and your work. I'd like to understand the photothermal processes for cancer therapy using the plasmonic materials. So actually someone injected some nanoparticles. There is a transmission by laser optically and there is an increase of temperature locally, I guess, because of the absorption. Yeah. So there is some plasmonics are nanoparticles are electron collective motion. In order to increase that temperature, we need some electron phonon interaction and some in order to increase locally the temperature. Is that the process, and how we control the step of transferring the energy from the electrons to the bulk?
Can I add something on this question, because I had something similar in order to not reply at the same time the same question?
Yeah.
How do you secure that the nanoparticles, they are going to be trapped by the cancerous cells and not, from somewhere else?
Yeah. Okay. Step by step. First of all, we are not performing experiments in mice yet. Okay. And they are not included in our two running projects. So this is the goal for our next proposals. So that's in order to answer first your question, Costa. So The idea here is exactly that you inject the colloidal nanoparticles close to the tumor. The tumorous cells are more sensitive to the temperature. It's actually what is very well known for the magnetic hyperthermia of cancer treatment. So the idea here is exactly that you can inject close to the tumor, and then you can exploit a near-infrared laser like a YAG in 1064, for example, because in this range, the tissues are transparent, so you can have delivery of the laser beam directly to the nanoparticles and not to the surrounding environment. So regarding the selectivity, Costa, both will be heated, but the cancer cells are more sensitive.
Yes,
So
this is true, because also from the photodynamic therapy we know this, that
exactly
the cancerous membrane of the cell is more ligand.
Exactly.
Yeah.
So regarding Nectario's question, the good thing with these materials, apart from being refractory, that means that they can sustain the high fields of the laser, apart of being able to tune the carrier concentration in order to have an LSPR in the near infrared without having some peculiar or exotic shapes and so on. The good thing with this material is that we do have very strong electron phonon coupling. I do have some references regarding this. So this is another asset for this category of materials instead of gold, which has been already used, but with some drawbacks, as I mentioned. So in this particular paper, there is a demonstration of gold, but for the case of, especially for titanium nitride, we have very strong phonon electron coupling. So we can indeed achieve that. I can send you, if you are interested, some
you know that we can measure that. We can measure. This is the reason I'm asking. We can measure that because we know that.
Okay.
That photothermia needs a temperature window. So we have to be very well someone very well know the physical processes in order to find the participation of how many material you have to inject in certain tumor and how much bigger.
That is very interesting, Nectario, because actually what I have in mind in terms of papers is just general experiments measuring optical spectra and Raman at various temperatures and so on. As far as I know, there is nothing specific to the treatment temperatures. So this might be really interesting.
And one more question, please.
Yep.
Yeah, it's very important for us that you can tune the frequency, the resonant frequency of these materials to be in the far infrared. Because as you know, there are a lot of different applications in this region, especially in imaging. You remember my talk, my last talk in Thessaloniki. We have there, we have a high harmonic generation source that filtering it in certain positions for imaging, it can be very important. So if you have already some materials that have the resonant frequency in the far infrared in the order of less than 100 or less than 100, I haven't seen less than 100, can be very important for our application. Just a comment.
Thank you very much, Nectarios, for the nice input, and Panos for the replies. And then the floor now is to Professor Kavoulakis.
Well, first of all, thank you so much for the nice presentation. I understand that these are very interesting results also from a practical point of view. By the way, we should all thank Kostas Petridis, who is kind enough to present me as a co-organizer, but he was the one who did all the work this year. So,
but you have inspired me. So you are inspiring me. So we are co-organizers.
So I'm not really in this field, but I wanted to ask you, I understand, as you mentioned, that you would like a material to have a dielectric function which changes sign and rather rapidly, actually.
Yes,
yeah.
Exactly.
If I could design a material by hand and do anything that I wish, do we have any insight of what would be the desired, property that we would like it to have in order to have this feature in terms of the dielectric function? I don't really have an insight, you see. I mean, I don't even know if there is an easy answer to this question.
Me either. I mean that usually what I have in mind is that these are actually, okay, these are experimental results, but in terms of designing these materials, the approach so far would be to have some band structure calculations by DFT, and then calculate the joint density of states, and from that calculate the epsilon 1 and epsilon 2, and have some predictions. Okay, we have done that, not by myself, I'm an experimentalist, but Christina Leka has done that in Yanina, and also Ravi Shankar now in upstate New York that we are working with is doing that as well. And this is a very good pre-screening of materials. But as I told you, in some cases, for example, like the tungsten nitride, it was expected because the calculations were done. Allow me just for one moment. Sorry, it's just that. Ναι, τελειώνουμε. Sorry, it's my wife, because again we have some problems of security in the campus, so she's calling me if I'm okay. I apologize for that, but yeah. So in the case of tungsten nitride, because in the calculations they were dealing with a perfect crystal, it was predicted that it would be a very good material, but then the experiments have shown that there are a lot of defects, which were okay. Afterwards, were explained again from new calculations, but from the beginning here for the case of tungsten nitride, we did have some problems. So I'm not expert in designing, frankly, I don't feel that I can give you a firm answer on that. So what I've done was just to calculate the band structure, and from that having a pre-screening of material, but so much, yeah, nothing more than that.
Okay, thanks a lot.
Thank you very much, Giorgos. I have one last question, if I may, because I understand that the situation is not so safe in Thessaloniki. Regarding the defects and the appearance of new plasmonic resonances, this seems that the defects, do they create any cavity effect? Because of the defect, you have some boundary conditions that it's like you're creating like something like a cavity. The refractive index changes, and this creates reflectivity or something like this, and you have these plasmonic resonances.
I don't feel that actually is a cavity effect, because this is really because they are point defects. So I would say that this is just the differences in the refractive index and so on is not a cavity effect because of the size, because of the scale. What I would say is that we do have a depletion from carriers, and this depletion changes actually the plasma.
Okay.
the dominant effect, I would say.
So you are based on your formula at the beginning. What is how the plasma frequency is defined by the concentration of the carrier.
Exactly the initial formula, as you very, very well noticed. So we are here, and so the dominant effect is that we change this N changes because of the depletion of carriers.
Yes, thank you. We have one more question from Dimitris Tsikridis. Please, Dimitris.
Yes.
Okay, thank you. Thank you for the nice talk. Let me ask you a simple question. There are also some other conductive ceramics like carbides or silicides.
Yep.
Are suitable for this application. Plasmonics or nitrides are better?
Yes, very good question. I did not include any carbides because actually we do not work so much with them. I would say that the carbides are of two categories. The one category is similar to nitrides, so they have a rock-solid structure, a 3D structure, and compared to nitrides, they are inferior because they have more electronic losses, so more damping. So they perform like the worst of nitrides, but there are the Maxine phases which are 2D, and these are really conductive, and there are a lot of people. For example, Yuri Gogotsi from Pennsylvania is working a lot with them, and these are really very promising. So in terms of carbides, I would respond, depends on the structure. So the 3D carbides are worse than nitrides, and that's why they did not receive so much attention. But the 2D Maxines are really very promising. Regarding the silicides, I'm not very familiar. I have the impression that the silicides have less carrier density than these nitrides, so they would be comparable more to the TCOs. So that means that they would have some resonance in the midIR and so on. So comparing the TCOs with silicides, I have not done that. So I cannot tell you if they're inferior or superior with TCOs, but I would say that the silicides are, from the optical point of view, closer to the TCOs than to nitrides.
Okay, thank you.
So, thank you very much.
Thank you very much.
Panos, for the honor.
I'm the last. Have a nice summer.
Yeah, it's the last one. Until the next one.
I bet you will do in Crete. So,
so thank you very much for the honor. All the participants for the participation.
My pleasure.
On behalf of me and George. And let's hope that we are going to meet again next semester with more colloquial talks from more fields. Thanks to your participation and your contribution and your suggestion. So,
thank you.
From the Sai Cafe, have a nice day and be safe, Panos.
Thank you. Thank you. Goodbye.
Bye.